next topic is automorphism of a groups. So let G be a group. Then what is the automorphism of G? So it is a set of all automorphism of a group G. So it means it is a set all F from group G to G, which is homomorphism homomorphism 1 1 and on to. So 1 1 and on to. So which is called a automorphism, set of automorphism. So set of automorphism is also a group under the composition of mapping. So this is also a group. This is also a group under composition of mapping, into composition of mapping. So remember that it is a all homomorphism 1 1 as well as on to. So this is called a set of automorphism, which is again a group. After that, so example number 1. Now we are discussing the group. So what is the example number 1? So in the given part, let G be a, this G be a finite abelian group. Finite abelian group, number 1. And number 2, if it is a finite abelian group, and number 2, such that order of G which is equal to n. So it is a finite abelian group of order n, where n is odd and greater than 1. So n is any odd integer, positive integer greater than 1. Then show that G has non-trivial automorphism. G has a non-trivial automorphism. So this is very important result, a very important question. It is our first question. Now, to prove this, solutions. So what is in the given part? So in the given part, we define a map F from G to G, and this map is defined by F of A, which is equal to A inverse. So F of A, which is equal to A inverse. So that is my mapping. Now, to prove that this mapping is a automorphism. So this to prove that this mapping is a automorphism. So we clearly prove that it is a automorphism, since when we take any two element, so let A B belongs to G, then F of AB, which is equal to AB inverse, so which is equal to B inverse into A inverse. Since it is a commutative, so this can be written as A inverse B inverse. So this value is equal to phi of A into phi of B, and it is for every AB belongs to G. So it means it is a homomorphism. And the second part, let f of A which is equal to f of B to prove the 1 it implies A inverse which is equal to B inverse. Now taking inverse on both sides, so A inverse raised to power minus 1 which is equal to B inverse raised to power minus 1. So it implies A is equal to B. So it means it is a 1 1. Now after that, to prove onto, so how we will prove it is a onto? So by taking for every, as we know that A inverse for every A belongs to G, there exists A inverse belongs to G such that f of A inverse which is equal to A. So it means f is onto. So this map is 1 1 homomorphism as well as onto. So it means this is a automorphism. So it means f belongs to automorphism of the G. So that mapping is clearly automorphism of the G. So my aim is to prove that G has a non-trivial automorphism. Now if this map is identity, now assume to prove it by contradiction. Now if this map F is equal to identity, so this map is automorphism of G. Suppose this map is identity, then by definition it implies f of A which is equal to I of A identity for every A belongs to G. Now substitute the value of FA, so which is A inverse which is equal to A. So what we get? We get A square is equal to identity for every A belongs to G. So what we get? We get this values. Now from this, order of A which divide 2, since 2 is prime number, so it implies order of A either it has value 1 or 2, since it is a prime number. If it is prime number, either it has value 1 or 2. So that's why how we can prove that if it is for every 1 or 2, for every A belongs to G. Now if order of A is not equal to 1, it means A is a non-identity. So what we get? If order of A not equal to 1, then it implies order of A is equal to 2. So it means if A is a non-identity, then its order is 2. So if order of A is 2, then it implies by Lagrange's theorem order of A divide order of G. So it implies 2 divide order of G, which is n, but n is odd, so which is a contradiction. So which is not possible. So which is not possible. If it is not possible, then it implies order of A is equal to 1. So it implies this A is equal to identity. So it means this A is equal to identity and order of A is equal, because order of G is 2 divide n and n is odd, but if 2 divides n, in that case it will be image. So which is a not possible. If it is not possible, then f is not equal to I. If f is not equal to I, then it means f is a non-identity automorphism. So it implies f is a non-identity. So if f is a non-identity, then it implies G has a non-trivial automorphism. Non-trivial automorphism. Non-identity. So it has non-trivial automorphism. So which prove our result. Now after automorphism, so we are discussing the next definition, so which is called a inner automorphism. So next definition, which is called inner automorphism. So inner automorphism. So this is my next definition. So what is inner automorphism? If I take some A element from G, what is G? G is a group. If G is a group, so define a map FA which is from G to G. So this is defined by FA of X. So this is a FA of X, so which is equal to this values, which is equal to AX A inverse for every X belongs to G. So this is equation number 1. FA of X which is equal to AX A inverse. Now to show that it is an automorphism, so first prove it is a homomorphism. So how it will be proved that let X and Y belongs to G. So FA of XY, so this can be written as AXY into A inverse, and this can be written as A into XY, so X identity Y, so this is X, and then this is identity that can be written as A inverse A into Y into A inverse. So this value can be written as XA A inverse, then again AY A inverse. So what is its value? So this is a FA of X, FA of Y. So this is for every X Y belongs to G, this values. So it means this mapping is a homomorphism. So that is my first step. This map FA which is from G to G. So this mapping is a homomorphism. Homomorphism. Now next is 1 1 and then on. So again I take FA of X which is equal to FA of Y. So it implies AX A inverse which is equal to AY A inverse. So since G is a group, so by left cancellation law, so this will be removed, and by right cancellation law, so this will be removed. So what we get X equal to Y. It implies this f of A is 1, 1. So this mapping is 1, 1. Now after that on to. So to prove on to, every element of G has a pre-image. So to prove the onto, we know that F A inverse X A. So what is this? This can be written as X. So this element has pre-image this element. So clearly this mapping FA is onto. Now it is 1, 1 as well as onto. So it implies FA belongs to automorphism of G. So this is called a inner automorphism. So inner automorphism can be written as I of G. So what is I of G? It is a set of all inner automorphism, inner automorphism for phism of a group. So of a group G. So this is a set of all inner automorphism of a group G. Now next theorem is to prove that the inner automorphism is a subgroup of a group automorphism of G. So to prove it is a subgroup, so next is the set, which is a set of inner automorphism I of G. So this I of G, which is a set of inner automorphism, is a subgroup of automorphism of G. So it is a subgroup of automorphism of G. Now solution. So first, non-identity I of G is a non-identity, should be non-identity, non-empty. So I take, since we know that FE. So what is FE? Basically it is an identity map. It belongs to I of G. So it implies I of G is a non-empty set. So this is a non-empty set. Now to prove the subgroup, I take two mapping. Let FA comma FB, it belongs to I of G. So what it means? It means FA of X, which is a X A inverse, and FB of X, which is B X B inverse. This values. It is for every X belongs to G. Now to prove subgroup, my aim is to show that FA into FB belongs to this, and FA and FB inverse belongs to this values, right? So to prove that result, first I prove FA into FB of X. If I take, so what is this? If I substitute the value of this, so this is a B X B inverse. Again I using this values. This value is AB, then X, then B inverse A inverse. So this value can be written as AB X, and this is AB inverse. So what it means? It means FAB of X. So this product, FAB of X. So it means multiplication of two mapping can be written in this way. Also, what is the inverse of B? So inverse of B, if I know that f of B of FB inverse, this value of X, so what it means? It means FB, and this is FB inverse of X. Now substitute its value. So this value is FB, and what it means? It means B inverse X into B, right? Now again operate at this point. So what we get? We get B inverse, then X, then B, and then B inverse. Now what we get? We get identity. This is identity, this is identity, identity, X, identity. So this value is equal to X. What it means? This is inverse of this and this is inverse of this. So we get FB inverse, this mapping inverse, basically it is a FB inverse, this values. Now to prove the subgroup, as we know that my aim is FA of FB raised to power minus 1. So AB inverse are these values. So in first step it can be written as FA of FB inverse by using this result, and this by using previous result, this can be written as FAB inverse. Now A belongs to G, B belongs to G, so this belongs to inner of, this belongs to inner of group G, since AB inverse belongs to G. Why AB inverse belongs to G? Because A is element of G, B is element of G, and G is a group, so it satisfies this property. So AB inverse belongs to G. If AB inverse belongs to G, so it means, so what it means? It means this FAB inverse belongs to I of G. So what we get? We get I of G, this I of G, which is a subgroup of group G, subgroup of group G, subgroup of group G. So this is my result. Now after that, the next theorem is show that, this is very important theorem, show that G by center of G by center of G, so this is isomorphic to inner of G, so set of inner automorphism of G. So that is it. So this result is GNDU 2015 and 2017. So this is my next problem, the next theorem. Now to prove this result, I will apply fundamental theorem of homomorphism. So define a map. So define a map phi which is from G to I of G, set of inner automorphism. This is defined by phi of A. So this is equal to f of A for every A belongs to G. Now what is Fa? So since Fa belongs to inner automorphism of G, so it implies Fa of X, which is equal to Ax A inverse. So this is a definition of inner automorphism for every X belongs to G. So remember that for every X belongs to G. So this is a definition of inner automorphism. Now, to prove that this mapping is homomorphism as well as onto. So I take two element AB belongs to G. So it implies phi of AB, which is equal to f of AB. Now, by previous result, this can be written as A into FB. So what is this? This is a phi of A into phi of B for every A, B belongs to G. So what it means? It means G, this phi is a homomorphism. So that is my first part. It implies this phi from G to I of G. So this is a homomorphism. 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 Now to prove the onto, so every number from the right hand side is onto. So clearly here it is FA, so that exists. So clearly we easily see that phi is onto mapping. Now it is homomorphism, it is onto. So by fundamental fundamental theorem of homomorphism, theorem of homomorphism, homomorphism, right hand side, which is I of G, so which is isomorphic to G by kernel of phi. So this is a G of kernel of phi. If I prove that it is a center of G, then I prove my result. So to prove it, kernel of phi, so let A belongs to kernel of phi. It implies this phi of A, which is equal to identity. What it means? Fa, which is equal to identity. So what it means? It means Fa of X, which is equal to identity of X for every X belongs to G. It means Ax A inverse, which is equal to X, and it implies Ax, which is equal to Xa. So if we multiply by, then it implies X belongs to G. So it implies this A belongs to center of G. Why? Because it commute with every member of G. Now reverse the process. If I reverse the process, what I get? I get kernel of phi is equal to center of G. So substitute that value, we get inner of G, which is isomorphic to G by center of G. So this is very important result. So in this way we can prove that this value is of this kind. Now we already know that as we did the cyclic group. So what is phi of n? So phi of n. So what is the phi of n? So it is the set of all integer m belongs to z such that GCD of mn is equal to 1, such that GCD of mn is equal to 1, where 0 less than m less than n. So it means m lies between 0 and n. So this is also say that set of all positive integer which are less than n and relative prime to n. Set of all positive integer less than n and relatively prime to n. Relatively prime to n. So this is called a Euler function. This is Euler's function.